So let's begin. First of all, if we talk about the surface of the planet, right, here, we should probably be able to identify the surface of the planet. And you notice one specific thing about this is that the graph stops, right, here. Let's put it in green. At this point, there's no more graph. And the reason there's no more graph is because you have reached the surface of the planet. You can't get any closer. That's why the graph stops there. So the potential on the surface of the planet is going to be this value here, right? So we're going to make this V S for surface of the planet, I guess, is equal to a negative, because it's a negative graph. And there's 1, 2, 3, 4 tick marks. Every tick mark is 0.1. Therefore, it has 3.9. The units are times 10 to the 8th joules per kilogram. This is the potential at the surface of the planet, just by reading the graph, right? Okay. If you want to go to the moon, you at the very least have to have enough energy to go from here all the way up and past this point, right? If you don't have enough energy to go there, to this point, well, you'll probably end up here, have no more energy, and what happens, you're gonna fall back to the planet, right? You're just gonna fall back to Earth. So the amount of potential that you need is up to here. This point here. And this potential is going to be V max, I guess. It's going to equal still negative 0.4 times 10 to the 8th joules per kilogram, right? The change in potential. Well, final minus initial. Final, here, negative 0.4 times 10 to the 8th joules per kilogram, minus the initial, you start here, negative 3.9 times 10 to the 8th joules per kilogram. So what is the change in potential? Well, positive 3.5 times 10 to the 8th joules per kilogram. But this is still potential, this is not energy. How do you get energy? Well, you want to get the joules, so you have to multiply by kilograms, right? The change in potential energy, or the energy required. Let's put E minimum energy. It's going to equal to the change in potential multiplied by the mass, and it's just a matter of multiplying by 850 kilograms, which is going to give you the minimum energy. When you do this, well, it's going to be 3.5 times 10 to the 8th joules per kilogram multiplied by 850 kilograms. This will give you 3.0 times 10 to the 11th joules. Right? In theory, it's not very hard. You just have to be able to know what the different parts of the graph mean. A lot of times, you'll see these graphs cut off. And the reason they cut off is because they reach the maximum limit. Well, in this case, they reach the surface. So you reach this value, this is the surface of the planet. You have to recognize that you have to go over this part, right? You have to know that there's going to be a difference in potential. You have to know that the energy is equal to the potential times the mass. Very simple, small concepts. If you string them all together, they help you solve the problem. Second thing is, well, where did they get this shape, right? Where you have the shape of a planet, the potential when you have a planet and the moon. Well, let's look at the shape more closely. So I'm going to paste it back here again. If you look at this shape, let's draw what it would have looked like if we just had the planet, let's say. And I'm going to draw this in orange. So if there was only the planet, it would be pretty much the same, except it would go like that. And wait a second. It will follow mostly the red line, except when it gets closer, it just goes like that. More or less. Just a second. Let me draw this again. Right? If you draw only the potential due to the moon, right? I'll draw this in green. It probably look something similar to this. And then it goes like that. Right? The red curve is just the sum of these two. So, this is one of the basic things is the total potential is equal to the sum, let's say the potential due to the planet P plus the potential due to the moon. Just add them up. The only difference being is that the moon is not at zero. It's at a different place. Right? Okay. Questions about this? Yes, go ahead. So let's look at the equation, right? Normally, if it starts at zero, let's think of it. The equation for the potential of the moon is going to be g. So the question that he asked is why doesn't it reach the Earth? And the thing is, it does reach the Earth. It's just so close to zero that I would just be drawing a straight line here, right? If we write the equation for the potential of the moon, it's going to gm, the mass of the moon, divided by r, right? This is if we started at zero. We shifted it, right? So it's going to be, instead of having r, right, it's going to probably be t minus r minus t, and t minus r, right? So this is a positive number between 0 and 1, right? When it's d, it's going to be 0. So you just shifted it, right? You shifted it by amount of d, and you flipped it over. The potential of the planet P is the same thing, just g, mass of the planet divided by r. This one just starts at 0. Let's see, are there any questions? Okay. If there are no more questions, we're going to move on to the next example. How can we use this? And there's a concept we call escape velocity.